So the first thing I'd like to do before we launch back into the lecture, remember the lecture we're doing is on electric fields. As I mentioned, we're going to stay on this lecture for quite some time. We probably won't get all the way through it until next week, so we're going to just keep chipping away at it today. But before we do that, again, I want to show you something, just a brief tour of Canvas. I know a lot of you have already checked out the Canvas page and you know where everything is. But in case you don't, I just want to point some things out so you know where to find things in the future. Because I've been getting a lot of emails just saying, where can I find the homework? Where can I find the lecture recordings and things like that? So I just want to clarify. All right, so when you log on to Canvas and you go to Physics 46, this is what you will see. At the very top of the page are some announcements. So basically, I'm going to post an announcement every once in a while just to let you know some things that are going on in the class and on campus. The most recent announcement is about an upcoming Women in STEM event, so you can check that out if you're interested. Okay, we also have a copy of the syllabus on the homepage. Just click there where it says click here for the syllabus. And one really important thing to know how to find is the lecture recordings. So on the homepage, there is a spot where it says click here to access the lecture recordings. So when you click that page, it takes you here. And basically, it's just a list of links that you can go to for each lecture recording. So every time I complete a lecture, I put it up on YouTube, and then I put the link on this page. So this list of links is just going to get longer and longer as the semester goes on. And I'll just put them in order so you can find it easily. Okay? So that's where you find the lecture recordings. Another thing to remember is it's always going to be super straightforward what we're doing in class each day, what we're doing in lecture and lab, as well as what assignments may be due. It's all in this schedule. So if you go to the home page and you just scroll to the bottom, the weekly class schedule is shown here. So I show you what we're doing in lecture each time we meet. And you can actually access the notes, that is the lecture slides that I go off of, using this table here. So just click on the link, it'll pull up the lectures that we're doing on that particular day. And same for the lab. This is what we're doing in lab. And you can click here to see what the lab handout actually is. Look at it in advance. And at the same time, we have a list of assignments that are due in the rightmost column. And this is just what I write on the board before class, right? So usually we're going to have some worksheet problems as well as some textbook problems. And you can always see what that is over here. So, any questions? Last thing to note, actually two more things to note. Any files that you might want to access on Canvas, just click Files here. There's a whole set of folders here. So one of the folders is the lecture notes, the other is the lab handouts, the worksheets that I pass out for homework, it's all here. So you can always access it. And the last thing I'll point out is the discussions. So if you click on discussions on the side of the page, these are these message boards that you can use to communicate with me or your classmates. So if you ever have a question about homework or anything else really, you can post a question here, and I'm going to be checking it very frequently, answering your questions. And if you think you know the answer to a question that someone's posted, you can also chime in there, okay? So that's pretty much everything I wanted you to know about Canvas and where to find things. So any questions before we launch back into the lecture? Okay, so let's just do a brief recap of where we stand as far as electric fields are concerned. We spent the last lecture, the one last Wednesday, going over how to calculate electric fields when you have multiple point charges. Okay, so I have a positive charge sitting here, a negative charge sitting there, any number of point charges. I know how to calculate the electric field. Okay, sometimes it's a tedious calculation, but there's a process that we should be familiar with by now. What I want to point out is that sometimes we're not dealing with just discrete little point charges. Okay, sometimes we're dealing with what's called a continuous distribution of charge. So think about, instead of just having a single charged particle sitting here and another charged particle sitting there, I just have a very, very large number of charged particles. Think like some kind of object you can hold in your hand that is electrically charged. We would not want to count up the electric field from every single electron and every single proton in that object. That's just not feasible, right? Because the number of particles involved is just so big. So instead what we do is we treat that object as if it's just a smooth distribution of charge. In other words, there's just some kind of electric charge spread out evenly, or maybe not evenly, depending on the case, throughout the object. Okay? And if we're doing that, what we'll have to do is bring in some calculus methods to calculate what the electric field due to that object actually is. So for example, let's say I have a triangle here, and I have some electric charge Q, which is just evenly spread out all over that triangle. And the question I might want to answer is, what is the electric field at some point away from that triangle? So the way I need to approach this is to break the object into infinitesimal charge elements. When I use the word infinitesimal, this should be bringing up calculus memories, right? In other words, we break it into tiny little charge elements, which I'll call dq for each one. Each one is approaching 0 in terms of how large it is how we treat this. So each one of these dq's on my object, each one of these charge elements, contributes something to the overall electric field. So let's just select one of these little charge elements, dq, on the object right here. And notice that it's a certain distance away from my point. So I'm going to call that r. Remember, r represents a distance between your charge and the point in question. And we also remember that electric fields, they point away from positive charges, right? And towards negative charges. So we'll assume, just for this picture, that this is a positive charge we're talking about. And so it's going to contribute an electric field that points just directly away from it. Okay? And I'm going to call that electric field dE. So how do I describe this thing dE? Well, dq, remember, is an infinitesimal amount of charge. So we can basically treat it as if it's a little point of charge. And remember, we know how to deal with the electric field due to a point of charge. It's given by Coulomb's law right here. It's k times the charge, which now we're calling dq, divided by r squared. And this r hat direction just means it's pointing away from the source of that charge. Okay? So that's just Coulomb's law, but we're writing it in what's called differential form because we have a tiny little charge element dq. Okay, so other than that, it's the same equation we've seen before, right? But here's the thing. I don't just care about the electric field due to this little piece of my overall distribution. I care about the total. So what do I have to do? I have to integrate over all of my dq's to find out what the total electric field is. So in other words, the total electric field is the integral of all of these little dE's, of all these tiny little electric fields, because I have to add them together to get the net effect. Does that make sense? So we have an object, we're going to break it into little charge elements, and then we're going to integrate to get the total electric field. That's sort of the name of the game here. And we're going to spend the entire lecture doing problems like this. I just want to give you some advanced warning. These are not particularly easy problems. Okay? They're pretty challenging. So I'll try to give you a lot of examples so you get a sense of how this works. Okay? All right, so moving on. Usually what we want to do, because remember, the electric field is a vector. So we can think of this vector as having an x component, a y component, and a z component potentially. And we really, in practice, want to treat each one of these components separately. In other words, I have Ex, that's the x component of my electric field. How do I get that? Well, if you look at the top of the page, I get that by integrating all of those little dEx's. So if I integrate all over my x components, I get the total x component. If I integrate over my y components, I get the total y component. And same for z. So potentially, we might have to be dealing with 3 separate integrals when it comes to calculating the electric field due to a distribution of charge, okay? But it's not that bad necessarily, because sometimes you can use what's called symmetry arguments to get around doing that integral. In other words, you can show that maybe one or many of these components is going to go to 0 due to something called symmetry. Okay, and I'm going to show you how this works with an example. Let's say that our distribution of charge is this. Okay, we have the x-axis and the y-axis, and in the xy plane, there's a ring of charge, and there's charge evenly distributed all over this ring, okay? The point I'm interested in is this one right here on the z-axis, okay? I want to know what is the total electric field because of this ring of charge at this point on the z-axis. So what I want to show you, and we'll draw a little picture to show that this is the case, that it doesn't really matter what point on the z-axis we pick. It's always going to be true that Ex is equal to 0 and Ey is equal to 0. And we don't have to do an integral to prove that's true, which is useful, right? Saves us a lot of time. Can anyone see right off the bat why that might be true?
They all cancel out.
There's some kind of cancellation going on, exactly, for those components. Let's see how that's going to work. So what I want to do is I'm going to identify a little dq1 on this side of the ring of charge. Okay, so this is just a little piece of the overall charge that's located on the left side of the ring. And we can show that there is an electric field due to that little element of charge, dE1, and remember it just points away from the charge. That's how this works. It's an electric field, points away from a positive charge. Now on the other side of the ring, I'm going to draw dQ2, which is just on the exact opposite side over here. Now, can someone indicate what direction generally is the electric field due to this guy going to be pointing in? It's like up and to the left, correct. Something like this. Okay, so we have dQ1 on this side creating this electric field. We have dQ2 on this side creating this electric field. Now, is it clear now why the x and the y components are going to cancel out? If I add these two together, the only thing I'm left with is a z component. Okay, I'm only left with something pointing along the z-axis. And because I can think of the entire ring as just being made up of these little pairs of dq's, right? Here's a pair, and so on. The whole thing works out so that the x and the y components all cancel, okay? So if that's not immediately clear, I'm just going to take it a little further and draw this out on a vector diagram, okay? So the two dE vectors that I drew, when we add them together, let's say we get something called dE total. So that would be my dE1 plus my dE2 from the picture, okay? And when I show these vectors added together, what I'm going to do is use the tip to tail method. So in other words, if you recall in the picture, dE1 is kind of pointing like this, up and to the right, and dE2 up and to the left like this. So this is what it looks like when they're connected tip to tail. We agree? So the total, the sum of those two, would just point straight up only along the z-axis. So the point is, there is a z component here. That's not equal to 0. But the x and the y components both are going to equal 0. And again, this is useful because for these two, we don't have to do an integral. If I wanted to know what the z component was, I would have to do an integral. But at least I can save myself some time for the other two. So are we all good on this so far? Okay, so let's keep it moving then. The next thing we need to get into is this idea of charge density. Remember, we're no longer dealing with individual point charges. Instead, we're dealing with charge smoothly distributed over some object. And there's three cases we're going to encounter. Okay? We're going to encounter one-dimensional charge distributions where everything is basically on a line. We're going to have two-dimensional charge distributions where everything is spread out over some area. And then we'll have three-dimensional charge distributions where the charge is spread out over some volume. So let's take a look at each one of these cases individually. So in the one-dimensional case, where we have charge spread out over a line, there's something called the linear charge density that we need to understand. And the linear charge density is just the charge per unit length on that line. Okay, so if we picture it this way, let's take a tiny infinitesimal piece of the line, and let's call the length dl. Okay, so that's what I'm highlighting here in the box is a small element of length dl. So in that length dl, there's going to be a certain amount of charge, dq. Okay, so if I just take the ratio of dq divided by dl, remember that's charge per unit length, that's what I call the linear charge density. And we give the variable lambda to denote that. Okay, make sense? Okay, let's say we have a two-dimensional distribution of charge, something that's spread out over an area. So in this case, imagine like a sheet or a plane of charge, and taking a little piece of that overall plane, a little bit of area. Let's call that area dA. So there's my tiny infinitesimal area dA. Well, in that area, there's going to be some amount of charge, right? Just like before, we'll call that dq. So the charge per unit area, dq divided by dA, is what we call the surface charge density. And it's given by this Greek letter. What is this called? Rho. That's actually, this one is sigma. Yeah, so sigma is dq divided by dA. All right, and then lastly, if we have charge spread out over a volume, okay, we can take a little tiny piece of that volume, which I'll call dV, and that's what we'll call our volume charge density when we do dq divided by dV. Okay, go ahead.
What's the three lines, the weird...
Oh, yeah. Does anyone know what it means when I, instead of say equals, I put like a triple equals sign? That just means it's a definition, okay? It's not like an equation that's giving you some new physics. It's just a way of defining what the variable is, okay? That's all it means. Anything else? Okay, so we'll move on. So this is our first real example where we're going to go through this whole process of calculating through integration what the electric field due to some distribution of charges. And in this case, we're going to look at an infinite line of charge. So here's the situation. Imagine all along the y-axis, we have a line of charge that stretches infinitely far in both directions. So it goes all the way up to positive infinity, and then all the way down to negative infinity. Okay, it's just infinitely long. We'll imagine that. We'll also say that there's a point on the x-axis, P, where I'm interested in finding the electric field. Okay, so here's my charge. It spans the entire y-axis, and I want to know what the electric field at this point here is. Okay, so this point, because it's on the x-axis, it has coordinates x, 0, 0. Okay, and also, if we want to characterize the charge that's here, we're going to use lambda. We're going to use a linear charge density. Okay, we're not going to put any numbers in here, by the way. We're just going to try to do this symbolically. We're going to try to come up with a formula in terms of all these different variables for what the electric field actually is, okay? So before we launch into that, I just want to see where your head's at. Can you think about, at this point, would any of the components be 0? So we want to say the y component is going to end up being 0 here. Okay, that is true, and I'll show you why that is from symmetry. Let's actually get into that now. Okay. So what I'm trying to show you here is just a simple argument that the electric field in the y direction is equal to 0. And here's why. This is our line of charge stretching along the y-axis. And it goes infinitely far in either direction. So obviously I can't draw the whole thing, but just it stretches infinitely far in all directions. Okay? Now, let's draw our point P right here. And let's do what we did before. Let's take a little dq. Maybe we'll take one up here to start. We'll call that dq1. All right? Now, what kind of electric field does that produce? Produces an electric field going directly away from it like this, dE1. Now, if I draw a second dq, which is an equal distance down from the x-axis, let's say dq2 right here, well, guess what? That's going to create an electric field pointing directly away from it, like this, which I'll call dE2. So I hope you can see just from this picture that the y components of these two cancel, right? And remember, even though we just picked out two little bits of charge on the overall line, the point is the whole line is made of pairs of charge like this that all cancel out. In other words, for every dq up here above the x-axis, I have one down here below the x-axis where the y components end up canceling out, okay? So we're all clear on that? So again, without doing any calculus, I can say Ey is equal to 0. It's also true that the z component is equal to 0. That one's actually simpler to argue. It's just that, remember, electric fields point straight away from the charge. So at this point, there's not going to be a component coming out of the page, right? So Ez is also equal to 0. So the only actual calculation we have to do is for Ex, okay? Because we've shown that the other components are 0. We only end up with an x component pointing straight away from the line of charge. Does that make sense? You with me? Okay, so now let's very carefully set up how are we going to calculate Ex. That's what we want. So let's draw a picture to start. That will help us. Okay, so what I'm going to do is copy down the picture from before. We have the y-axis here, and we have the x-axis here. And this is the point on the x-axis where we want to calculate what the field is, okay? And remember, on the y-axis, we have a line of charge extending infinitely far in both directions. So obviously, I'm not drawing the whole line, but there it is. Okay, so I'm going to start, just like before actually, by selecting a little dq, a little bit of charge along the line. So that little shaded region is my dq. And I'll label it as such. Let's also notice that the dq extends a little bit of distance on the y-axis, okay? So I'm just going to label that distance dy. Does it make sense why I would do that? Because it's an infinitesimal distance on the y-axis. All right? So next thing I'll do is I'll just draw an arrow which tells me what is the electric field created by that little dq. And remember, that's what we call dE in our picture. Okay? But let's keep in mind, I'm only interested in the x component. I've already done the work to show that the y and the z components both come out to 0. So what I'm going to do is just label the x component now, which is this, dEx. That's the only one I should care about, just the component that goes on the x-axis. Okay? Now, how would I break things down by component? Well, I first need some kind of angle. So let's label an angle here, which we'll call theta. And then let's also notice that the same angle appears over here. All right? Also notice we've got a nice right triangle. That might be useful. So what I'll do is label the sides of this right triangle. So x is this side. It's just the distance from the line to the point in question, okay? This distance is y, just the distance down to where my dq is, okay? And then this distance, the long distance that I've shown with the dashed line, what would I call that? What variable do we?
R?
Yeah, that's r. Remember, r represents the distance between my point and the charge, okay? That's what r means. Okay, so now that the picture is set up, we can start writing down a couple equations. Let's start with this. Let's say dEx equals something. What does it equal? It equals the magnitude of dE times what? If I take the magnitude of dE times cosine of theta, that would pick out this x component. Do we all see that? Okay, good. How do I write the magnitude of dE? It's Coulomb's law, right? We have an equation. If you have a tiny bit of charge, the electric field it produces is going to be K times Q, but in this case we're going to write dQ, just to keep the convention going, divided by R squared. Does that make sense? So the strength of this electric field overall is just given by this familiar equation. Okay. So here's what we should do next, okay? I want to find EX. And that means I need to integrate all my DEXs. Okay, and include all of the charge on the line in that integral. So the question now becomes, how do I write everything in terms of just one variable that I can integrate over? At this point, that should be our goal. And it's kind of a mess now because we have so many different variables floating around, right? So I'm going to suggest that we try to write everything in terms of the variable y, okay? We just integrate over y, and how does y go? Well, it goes from minus infinity down here to positive infinity up here, right? And if we can write everything in terms of y, we'll have an integral that we can actually evaluate, okay? So that's the goal. So let's start doing that. Let's write r. How do I express r in terms of y? So just by the picture, what? Yeah, r is the square root of x squared plus y squared, right? It's just a Pythagorean theorem. And note, x is just a constant. That's just how far away from the line I am. Y is not a constant because there's different values of y along the line, okay? So this is good. What about, I don't know, cosine of theta? That's another thing that's appearing. Maybe I want to get rid of cosine theta. What should I do? Yeah, so here, if we take a look at this triangle, x is my adjacent side, and r is my hypotenuse, and cosine is adjacent over hypotenuse, isn't it? So this would be x divided by r, or x divided by square root x squared plus y squared. Okay, so it's looking better now, because this r is now just in terms of y, and this cosine theta is now just in terms of y. And then, of course, the constant x. What else should we do? Well, let's take a look at dq now. Let's try to substitute that out in terms of my y variable. That should be the goal next, okay? So let's remember, lambda is our charge per unit length along this whole line of charge. And it's assumed here that that's just uniform, so it's evenly spread out over the line. So how do I write this in terms of the variables you see in the picture? What is my charge that goes on top of this ratio? dq, right? What's my length? I'm gonna call it dy in this case, right? Because it's the distance on the y-axis. Does that make sense? So dq over dy is lambda. Therefore, dq is lambda dy. That's great, because now I have dq in terms of my y variable, okay? So let's try to put that all together real quick. Let's say, remember, dex, what did we say at the very top? That's the magnitude of dE times cosine of theta. The magnitude of dE is k times dq, which I'm going to sub in as lambda dy, so that's k times dq right there with the substitution, divided by r squared, where r is the square root x squared plus y squared. And I'm going to square that whole thing. So again, that's k dq divided by r squared with the substitutions. But that also is multiplying a cosine theta, isn't it? So what am I putting in for cosine theta? This right here. This is x divided by square root x squared plus y squared. So let's just collect things so we know what to do. So first of all, I have some constants. K is certainly a constant, lambda is certainly a constant, and so is x. X is just telling me where my point is. Yeah, go ahead.
How is lambda a constant?
It's just how much charge there is per unit length. So like, it doesn't matter if I pick a dq over here or up here or anywhere on the line, we're told that lambda is just the same everywhere. Okay? In other words, that's another way of saying the charge is evenly spread out. It's not more clustered in one region of the line or another. It's just evenly spread out. That doesn't have to be the case, but in this problem, that's what's going on. Okay? All right, so these are the constants I'm pulling out. And then what do I have? I have a dy on the top. Can I write this in a more sensible way? Basically, I have square root x squared plus y squared, and I square that, but then I have another factor of that. So I can write this, if I wanted to, as x squared plus y squared to the 3/2 power. That's what's on the bottom of this, okay? All right, so again, I just want to point out that these are constants right here. Okay, cool. So if I want EX then, that's going to be the integral over all of these DEXs, which I should move up here, okay? And basically, what I'm integrating is this big expression that we wrote down, okay? But like with any integral, if I have some constants, I can pull them out. So I'm going to do that just right away. So I have k lambda x, and then I have the integral of what's left, which is dy divided by x squared plus y squared, 3/2 power. I need limits of integration now. What should my limits of integration be? Remember, I'm integrating over y. Say it again? So it should be minus infinity to infinity. Because remember, the idea is this line of charge extends infinitely far in both directions. So that's our integral, okay? So I want to point something out here. At this point, I'm not saying the rest is necessarily like the easiest thing in the world, but I think the hard part of this problem is to get here where after this step, I can just do the integral, okay? And we do have limited time. So what I'm going to do just for this one is tell you what the answer to this comes out to be, and then we'll go from there, okay? So this integral, if you type it into Wolfram Alpha or something, or if you actually grind it out, it's not too bad, it just takes a little time, is 2 divided by x squared, okay? That's what this works out to. So therefore I have k times lambda times x times 2 divided by x squared. That's the result of the integral. So what do I have? I have 2 k lambda and then x on the bottom. And just remember, x is how far away from the line of charge I am, okay? Lambda is the charge per unit length on the line, and k is just a constant that we find in Coulomb's law. So if I wanted to plug some numbers into that, I could. But this is the expression. Okay. I know it's kind of a lot, so any questions so far? We'll keep going with some more examples. Okay. Okay then. So just to recap what we did in this problem, we integrated to find the total electric field on this line of charge. And we found, just by making symmetry arguments, that the y and the z components both came out to 0. The x component did not come out to 0, so we actually had to grind through the integral to get it. But when we did, we got 2k lambda over x. I just want to remind you that k is sometimes written as 1 divided by 4 pi epsilon naught. So if we plug that in, we'll just get this expression right here, which is lambda over 2 pi epsilon naught times x. Okay? Okay. So we'll keep it moving. Now this one, I want you to, at your desk, make a drawing of some electric field vectors and try to answer the question that way. You don't have to do an integral, just make a drawing and it should be clear enough. So here we have charge Q uniformly distributed on a ring that has a radius of r, and it lies in the xy plane. Okay, the center of that ring is right at the origin of this coordinate system. So I'm asking you now about the origin, which is right in the middle of the ring. What is the total electric field there? In other words, if I take a look at the components Ex, Ey, Ez for the electric field right here, which one of those are going to 0? Okay? So what I suggest is make a drawing where you show a little dq on one side of the ring, a dq on the opposite side, and see if there's any kind of cancellation happening, and if so, which components are canceling. Okay? So take a few minutes to make that drawing, and then we'll go over it. And as always, talk about it with people next to you. Remember, this one's actually very low. This is this point, in other words. So you're right about x and y canceling. Zero is but if you were to come up or down, yeah. Okay, so anyone want to shout out what the answer is? All of the components are actually 0 at that particular location, okay? So I think the easiest way to see this is, let's, it's kind of hard to visualize a 3D drawing when you draw it on a 2D piece of paper. So let's take the perspective of looking down the z-axis into this plane right here, okay? So that's what we'll do. And so what we're doing is we're looking down the z-axis into the xy plane, which is where the ring actually sits. It's in the xy plane, okay? So there's the xy plane. There's the ring, with the center of it being at the origin. Okay, so remember, the idea would be, I'm going to draw some element of charge here, call it dq1, and indicate that it's creating an electric field over here, which I'll call dE1. And remember, the point we're interested in is the origin, so that's why I'm drawing it there, okay? Now on the very opposite side, I have an equal amount of charge, which I'll call dq2, and that's creating an electric field going in the exact opposite direction, dE2. So there's actually complete cancellation. All components are canceling, right? Because I have basically two vectors pointing away from one another, which have the same magnitude, because everything is symmetric. Does that make sense? So therefore, at least at the origin, EX, EY, and EZ are all 0. Okay? But if I were to come up off the off the z-axis going up or going down, then it wouldn't be 0. Okay? Then you'd have a z component. Okay. So let me just do one more of these. This one's a little tougher. And again, this doesn't require any kind of calculation. It's just, can we see from symmetry which components are going to 0 in this situation, okay? So in this situation, we have a half ring of charge. So it's not a full ring, it's just a half ring. And this one happens to lie in the xz plane. So you see that? There's my half ring of charge in the xz plane. And then coming out this way is the y-axis. There's a point P on the y-axis, and same question, right? What does the electric field look like there? Not anything too specific, just can we identify components that go to 0? Okay? So try this one out, see what you come up with, and then we'll go through it together. And if it helps, here's the suggestion. Try maybe drawing two pictures. One, where you're looking at this ring from the side, you're looking at it kind of edge on. Then try another picture where you're looking at it down the y-axis face on. And see what you can determine from looking at it from those two different perspectives. All right, so how about we do this one by like a show of hands, okay? So raise your hand if you think each component is going to 0. Who thinks EX is going to 0, the X component? Who thinks the Y component is going to 0? Okay, a couple people. Who thinks the Z component is going to 0? Okay, so the consensus seems to be, there's a little disagreement, that is just the X component going to 0 and nothing else, and that's correct. Let's see why. So what I suggested that you do is to draw two pictures, so I'll do that here. Let's look at this ring from the side. Okay, so we'll just be seeing it edge on like this, where this is the z-axis coming up, this is the y-axis extending out away from the center of the ring, and then we'd be kind of looking into the x-axis, so the x-axis is coming out of the page at us from this perspective. Does that make sense? Okay, so just pick, any DQ on this ring, let's just say that one, and we'll draw the electric field that it creates at our point on the y-axis. So actually, let me actually extend the y-axis a little further to make this work. Okay, so there's our DE. What I'm going to do is label two components here. Okay, I'll call it DEY. That would be my y component, right? But this part right here, I'm going to call it DE perpendicular. So it's perpendicular to the y-axis, but it actually includes both x and z components, okay? So to see how that kind of looks, again, we're going to take a different perspective where we're looking at the ring face-on, down the y-axis. So we're looking down the y-axis, seeing the ring face-on now. So we'll see the half ring looking like this. We'll see the z-axis here, and we'll see the x-axis here. Okay? Now, what I'm going to do is make an argument from symmetry that the x components are going to cancel if I draw a DQ over here and another one on the opposite side over here. So just like before, let's draw the electric fields created by each one. So it's not a perfect drawing, but I hope you see that this DE2 and this DE1, they don't completely cancel, right? They only cancel in their x components. So therefore, EX is equal to 0. But they're not canceling in their z components, are they? So I don't want to see the z. I don't want to say that the z component is going to 0. And at the same time, if we look at this picture, there's nothing that cancels the y components either. So it's only x that's going to 0, nothing else in this particular case, okay? So it's important to be able to know how to do that kind of thing. Just we want to avoid doing the integrals if we can, just to make our lives easier, okay? Well, sometimes you can't avoid it. Okay. So with that said, let's move on. Here, we're going to go back to a problem that we already looked at, except we're not just going to ask what components of the field go to 0. We're going to actually integrate to find out what the field is. So remember, this is the situation where we have a ring of charge which lies in the xy plane. The radius of that ring is capital R. We're going to use capital R for the radius going from the center to the edge. And we're going to say the total charge on the entire ring is Q. So there's a point on the z-axis just above the center of the ring. And what I want to determine is what is the total electric field at that point. Okay? So we've already done some of the work on this problem, haven't we? We've done the work of saying there are certain components that go to 0. Can you just remind me which ones are going to 0 in this situation? Yeah, x and y components are going to 0. The only thing you're left with is a z component in this case. So all we need to do is calculate the z component, because that's all there is. Okay? So let's do that. So we have to make a very detailed picture to get this right. This is always how these problems are going to start. So let's draw the z-axis going up. And then down here is the xy plane. And in the xy plane, centered at the origin, is the ring. Something like this. That's good enough. Okay. What do I do next? I want to basically identify on this ring an element of charge dq, okay? So it doesn't really matter where I put that element of charge. Let's just say I'll put it here. There's my dq. All right? And I want something that's going to help me sort of locate where that charge is. So what I'll do is I'll draw a line going from the origin to my charge dq. By the way, the radius of the ring is capital R, so that would be that distance along the line. And there's also an angle that takes me to where the dq is. You see that? There's an angle in the xy plane. I'm just going to call that, for the sake of argument, phi. All right? And there's something else I should note about my charge dq, okay? Like, it takes up a certain distance, doesn't it? I could say it has a certain length, or I could say it spans some angle. Okay, what I'm going to say about dq is it spans an angle d phi. And that's going to be a tiny little angle because, of course, dq is a tiny bit of charge. Does that make sense what I just said? So it's got a tiny little angle that it spans on the ring. Okay? And we're calling that d phi. All right. What can we do next? Well, let's now go to the point on the z-axis where we're interested in calculating the field. So there's our point. So if I draw a line like this, going from my dq all the way up to that point, what is the distance here? What do we call that? We're going to call that small r. Remember, small r is how far away is your charge element. That's what it means in our equations. Okay? And actually, you know, we have a nice little right triangle here. This distance is z. All right, that's how far we go along the z-axis to get to the point. So notice we have a right triangle. I'm actually going to copy that right triangle just so it's clear. Where we have R, capital R, for the radius, z for the distance up the z-axis, and then lowercase r for the total distance to my charge. Okay? That makes sense? Okay. So what do we do next? We draw the electric field dE created by that little bit of charge dq. And remember, we don't care about every single component of that vector. We just care about the z component. So now, why don't we label what the z component is on our picture? This is how I see the z component. It's just how far along the z-axis does this project. So I'll call it DEZ. Okay? Now, if I wanted to get that component, it might be helpful to know a certain angle, namely this one right here. I'll call that angle theta. Okay, so it's different from phi. It's the angle my DE vector makes with the z-axis. Okay? And notice I have that same angle down here, which is in my triangle, so I'll label it right here. Okay? So there's our setup. We have the picture now. With this picture, we can start writing down equations. So any questions about how I'm setting up the picture before we do that? Okay then. So let me remind you, we only care about the z component DEZ. That should be the magnitude of DE times what? Going off this picture here.
Cosine theta.
Yeah, it'd be cosine of theta. The reason for that is you have a right triangle where the magnitude of the vector DE is my hypotenuse, and the adjacent side is DEZ. And remember, adjacent goes with cosine. That's how we get this. Okay, so that's a good start. We'll also remember that magnitude DE is just given by Coulomb's law. We have K times dq divided by r squared. That's how we just say what the magnitude of dE is. Okay? So at this point, our goal should be to pick some kind of variable that we can actually integrate over. Does anyone have a suggestion? There's a lot of variables floating around. But which one can we integrate over so that basically we include the entire ring and not just some little piece of it?
Z? No.
So z is fixed actually. That just tells us how high our point is. In other words, I want some variable that allows me to go all the way around the ring. Phi. Phi should be my integration variable. If I integrate over phi, then I can go all the way around the ring and include the entire charge distribution. So that's my goal. It's just to kind of write everything in terms of phi if I can. Okay? So let's do that. So remember, I'm just going to write something that we are given in words. The charge is uniformly distributed on the ring. So it's evenly spread out all over the ring, in other words. Okay, that's what we know. I can actually take that and turn it into kind of an equation. So let me write the equation in words. This equation says that the angle element, that is just a little angle spanned by my dq, divided by the total angle, which is the total angle if you go all the way around the ring, that should equal my charge element divided by my total charge. So if this isn't clear yet, let me just give you some examples, right? Let's just say for the sake of argument that my dq, it spanned 1/10 of the ring, right? Well, because the charge is evenly spread out, guess what? It's going to have 1/10 of the charge too. So whatever fraction of the angle it spans, it has that same fraction of the charge. That's what it means to be evenly spread out, right? So I can write this as d phi, that's my angle element. What's my total angle? That's what goes here. It's 2 pi because we go all the way around the circle. Okay, that's important to note. That's 2 pi. What does that equal? My charge element, what do I call that? dq. And then what's my total charge? We're just calling, in this problem, we're just calling that q. Okay? So are we clear on how this comes about? And the reason I'm doing this, by the way, is because now I can write dq in terms of phi, because dq is, we solve for it, big Q divided by 2 pi times d phi. And Q is just a constant, that's just how much charge there is, and so is 2 pi. Okay? So we have that. Okay. Next, let us try to sub a few other things out. From my triangle, how can I write the distance to my charge element, which I'm calling lowercase r?
Z squared plus R squared, or the square root of that?
Okay, z squared plus big R squared. So remember, z is just how far up the z-axis do we go to get to this point, and big R is the radius of the ring. Both of these things are constant, okay? We square root that. So actually, those are just two constants, z and capital R. Next, let us rewrite cosine of theta, because that appears in this equation here. We want to sub that out maybe. How can I write cosine of theta using the triangle here?
Z over R.
Yeah, so it's my adjacent side z divided by lowercase r, which is my hypotenuse, right? And I can write that as z divided by the square root of z squared plus big R squared. Again, that's the radius right there. Okay, so what I want to do next is write dEz, making all these different substitutions. Remember, what are we putting into this? We're putting magnitude dE, which is given by this expression, given by Coulomb's law. Let's write it out. That's k times dq. What am I putting in for dq? I'm putting in this which is q over 2 pi times d phi. So that's k dq. I'm going to divide r squared. The r in Coulomb's law is this. It's the square root z squared plus big R squared. And you got to square that whole thing, right? So in other words, I made this substitution at the bottom. But that multiplies cosine of theta. And as we just said, this substitution right here can be made for cosine of theta. So that's going to be z divided by square root z squared plus big R squared. Okay, so there's a lot going on here. Let's just collect the terms. And what I like to do at this point, because we're constructing the thing that we're going to put into the integral, right? I just want to make note of what is constant in this expression and what is not, okay? And the spoiler is that there's actually only d phi that is not a constant here. You see that? Because we have k, we have the total charge q, 2 pi is just a number. Remember, z is a constant, that's just how far up the z-axis we go to get to our point, and so is the radius of the ring. So this one is actually pretty nice in that, you know, it's a little challenging to set up, but once we integrate, it's really trivial. So here, what we have is, on top, we have k and q and z, right? K, q, and z. On the bottom, we have 2 pi, and then all of this combined together can be written as z squared plus r squared to the 3/2 power. And then just d phi. So these are all the constants. Okay? So the last thing we do, now that we've constructed what goes inside the integral, is to actually do that integration, which says ez, super easy, right, is integral dez, which is this whole thing we wrote down, okay? And right away, I'm just going to pull out what's constant, as we said before. So that's kqz divided by 2 pi, z squared plus r squared, 3/2 power. The only thing in the integral that I was not able to pull out is d phi. And what are my limits of integration? In this case, it's just an angle, and we want to go around the circle, so it's going to be 0 to 2 pi. Okay, 0 to 2 pi. And you know, what does that actually work out to right here? This 2 pi, right?
Yeah.
That's a pretty trivial integral. It just works out to 2 pi. And that 2 pi cancels with that 2 pi, doesn't it? So what we're left with is just this. You have kqz divided by z squared plus r squared, 3/2 power. And that is it. Okay? All right, so let's just summarize what we did, okay? By symmetry, at this point right here, the x and the y components of the electric field are 0. The z component, which we calculated, is this. We write that as kqz divided by z squared plus r squared, 3/2 power. But remember, k, if you want, can be replaced with 1 over 4 pi epsilon naught. So that's all I'm doing going from here to here.
What's epsilon naught again?
Yeah, epsilon naught, k is a constant you've probably been plugging in a lot in your homework problems, right? Epsilon naught is just a different constant, but k is equal to 1 over 4 pi epsilon naught. So in other words, there are just two sort of conventional ways we write Coulomb's law to describe electric forces. One of them involves the constant k, and the other involves this constant. I don't want to really get into like the reasons why. Hopefully that will become clear in the next chapter, Gauss's law. But for now, just it's two different ways of writing the constant. Okay?
And this would be the electric field that you would feel in the z direction.
Yeah, so if you're right here, there's just an electric field pointing up like this in the z direction, and this is how you would calculate exactly what number to assign to that. It's using this formula.
Let's say you have a, then you have to go all over the step or just dropping easy or what you have there.
Are you saying if you have like another ring problem?
Yeah. we
So
have
on the
to go
homework, I
all
really
the
want you to like go through the steps of setting up the integral and doing that. So yeah. So actually work it out from scratch. Okay, anything else? All right. So we're gonna just keep going ahead with another example. And this example is a disk of charge. So what we dealt with just before was a ring of charge. So that was basically like a one-dimensional object, right? Now we have not a ring, but a fully filled out disk, okay? So now the charge is not spread out over a line, it's spread out over an area, okay? So the situation is this. The radius of this disk, which lies in the xy plane with the center at the origin, is capital R. So we're kind of using the same variables. But just remember, instead of being completely hollowed out with nothing on the inside, it's totally filled out. So because we have charge sitting on the disk over an area, what we're going to use is, remember, this thing called the surface charge density. That's sigma. So sigma is the charge per unit area. That's what it means. What we want to do is we want to calculate the total electric field at this point right here, P. Okay? So it's not going to be the same exact result as before, because again, this is a fully filled out disk, whereas before we were dealing with a ring. However, we are going to use the result from before with the ring to do this calculation. And here's how that's going to work, okay? How can we build up the fully filled out disk? One way to think about it is to put a bunch of rings together. Start with a really small ring at the center. Then have one around that, another around that, and just keep going, and eventually you've constructed the disk, right? In other words, you try thinking of the disk as being made up of rings that are all concentric with each other. Does that make sense? So we're going to build up the disk by adding together a bunch of rings, which is useful because we know the result for a ring, okay? So that is our strategy going forward. Okay, so we're gonna work this out on the document camera. So let me just explain in words what we're doing here once again. We're gonna divide the disk into rings, okay? And these are gonna be infinitesimal, by the way. The radius of each ring, I'm going to call capital R. Sorry, lowercase r, right? I'm going to call the thickness of each ring dr, okay? And I'm going to call the charge on each of these rings dq. Okay, so let's draw the picture. I'm looking down the z-axis at the disk of charge. So here is the fully filled out disk like this. Okay, this is the view looking down the z-axis. Okay, what I'm going to do next is indicate that the radius capital R is just the full radius of the disk, right? That's what we mean by capital R. But next, I'm going to show you one of these rings of charge that we use to build up the disk. So I'm going to show that with like a dashed line. How about something like that? But I want to show that it has some, thickness to it. So this is one of my rings. Okay. I'm going to kind of fill it in so it's clear this is what we're talking about when it comes to one of these rings, okay? So like I said, This has a radius, which I'm going to call lowercase r. So I'm going to indicate that right there. And it has a thickness, which I'm going to call dr. Okay, so the thickness of this thing is dr. Now, it's infinitesimal, so that thickness is going to be going to 0. But I just want to indicate it for you here so you can see. Okay? So, each ring contributes a certain amount of electric field, doesn't it? We've already calculated what this is. I'm going to show you what the result is. It's going to be, what do we have? We had K, actually here, sorry, I'm not going to write it that way. I'm going to write it as Z times Q divided by 4 pi epsilon naught times Z squared plus R squared, and then we take that to the 3/2 power. Now let me just explain where this came from. This came from the previous problem, right? This is the previous problem where we figured out the electric field due to a ring of charge, okay? But now the ring of charge has radius lowercase r, so that's what we're putting downstairs. And also, the charge that is contained on that ring, now we're calling it dq as opposed to just q, because it's an infinitesimal amount of charge. Okay? But it's basically the same result from before, just writing it slightly differently. So that's the electric field contributed by each one of these rings. What do we want to do? We want to integrate over all the rings to get the total electric field from all of them, and that will be the disk. Okay? That's where we're going. Okay. Let's do a little bit of work on this then. I want to rewrite dq in this formula. Okay, and the way I'm going to do that is to use the idea that this disk here has a surface charge density, which we're indicating with sigma. Okay? This surface charge density is the charge per unit area. So in other words, if I take a look at this little ring that I drew, it would be the charge on that ring, dq, divided by the area of that ring, dA. Does that make sense? dq divided by dA is just the definition of sigma. But, okay, if we look at this ring here, can anyone think of like a formula for what the area of that shaded in ring would be? It might not be immediately obvious, so I want you to visualize it this way.
Maybe the washer method?
So, yeah, it's something like that. So imagine taking this ring and kind of unfolding it and laying it flat. So can you visualize that? Like cut it right here, kind of lay it flat on the table, so that ring now becomes like a rectangle that we've just laid flat. Does that make sense? So that rectangle is going to look something like this. This would be the thickness of the ring dr. You see that? What would this distance be? Yeah, it's the circumference of the ring. When we lay it flat, the circumference just becomes the length, okay? What's the circumference? What's the formula?
2 pi r.
Just 2 pi r. So what's dA? What's the area of this thing?
2 pi r times dr.
2 pi r dr. So going back up here, sigma, which is dq over dA, is just dq divided by 2 pi r dr, just making the substitution for dA. Go ahead.
Wouldn't the length of the rectangle be the diameter, not the circumference? Because circumference is the...
Diameter is from this end to this end, but we're laying the whole thing flat. We're unfolding it. So it'd be the
You're
circumference.
holding it, okay.
It'd be the distance all the way around, laid flat. Yeah. Okay. So with this, we can say dq is sigma times 2 pi r dr. Okay, so we use the definition of surface charge density to re-express dq as this whole thing. Okay, that's what we just did, just to be clear. So, back to our electric field expression. DEZ is equal to z times dq, where this is the substitution for dq, it's 2 pi, it's sigma times 2 pi r dr, right? Just subbing that in right here, divided by 4 pi epsilon naught z squared plus r squared to the 3/2 power. Now, this is looking a little messy, but this is useful now. Because if we write this with some of the constants kind of separated out from the rest of the expression, remember, z is a constant. That's just how high up on the z-axis we're going to get to our point. So that's always going to be the same regardless of what ring we're choosing, right? We also have sigma. We also have a 2 pi on top and a 4 pi on the bottom. So that's just a factor of 2 on the bottom, right? I'm just using epsilon naught here, so that's a constant we can identify 2. And then what are we left with? On top we have r dr. On the bottom we have z squared plus r squared 3/2 power. And just notice that these are constants. Okay? So now we're making some progress because we can actually integrate this thing to get the total electric field due to the disk. Okay? And the way we're going to do that is we're going to integrate over lowercase r. Remember, the way we set this all up is lowercase r is the radius of our ring. So we want to include the entire disk. We want to start with r equals 0 basically, and then we want to go all the way out to the edge, which is capital R. Does that make sense? So we're integrating lowercase r from 0 from the very center all the way out to the edge, which is capital R. That's how this is going to work. Okay? And that way we include all of the charge on the disk. That's the whole point. Okay? So pull out the constants, which are z sigma over 2 epsilon naught. Take the integral from 0 to capital R to include every bit of charge, and then just write what's left over. R dr divided by z squared plus r squared to the power 3/2. Okay, let's actually just go through this integral real quick. This is one that won't take too long to do. Anyone know how to approach this? There's a little trick, an integration trick we can use here. U substitution. Yep, that's right.
Yeah, but on the previous one, we were saying that was the constant too. It was a distance.
Yeah, so in this case it's not, because when we just have a single ring, the radius of that ring is just fixed. But now we're saying we're taking all multiple different rings, and the radius is going to increase as we go up. Yeah, so it's not a constant. Okay. Good question though. That's the tricky part of this, is to know what's constant, what's not. Okay, so here's what I'll suggest for the U substitution. I'm going to say U is equal to Z squared plus R squared. In other words, U is just what's in the parentheses right there. And that means du, or let's just say du dr. Let's take the derivative of that thing. How do I take the derivative du dr of this expression? What does it give me?
2r.
Yeah, so z is just constant, and then the derivative of r squared becomes 2r, which means r times dr, which is what's upstairs here, is equal to what? So if I take r times dr and solve for it, I'll have du divided by 2. Do y'all see that? So I'm subbing this in for u, I'm subbing this in for r dr. So I've gotten rid of everything except the u variable when I do that. You see it? Okay, let's also discuss the limits. So like if my R limit is going to 0, then my U limit should be going to what? In other words, if I plug in 0 into this expression, what do I get? I get z squared plus 0 squared, which is z squared. So my bottom limit, if I'm using the u variable, is z squared. Does that make sense? When you do a u substitution, remember you have to change the limits of integration as well. Okay, my top limit is little r is going to big R. And when I do that, u is going to z squared plus big R squared. So that's the substitution, and that's how we change the limits in light of the substitution. So now let's implement it. We have ez equals, I have the same set of constants out front, which are z sigma divided by 2 epsilon naught, okay? Then, in place of r dr, remember I'm replacing that with du over 2. In place of z squared plus r squared, I'm replacing that with just u. And what power is that to? It's the 3/2 power. What are my limits? Again, bottom limit is going to be z squared. Top limit is going to be z squared plus r squared. All right, so I have the factor of 2 from inside the integral that I can pull out to say the constant out front is z sigma divided by 4 epsilon naught. So just combining that factor of 2. I have z squared to z squared plus r squared. If I have u to the 3/2 on the bottom, that's like saying u to the minus 3/2. I like to think in terms of powers, so I'm going to write it that way. And, okay, we've turned this integral, which looks kind of ugly, into just a power rule type integral. Remember, if you just have a variable to some power, that's it. There's just a simple power rule that we can use to calculate what the integral is. Do you remember how that goes?
Add 1 and divide by the result.
Yeah, pretty much. So here, constants out front are z sigma 4 pi epsilon naught, right? This thing integrates to minus 2u to the minus 1/2. Basically, when you integrate a power, the power just goes up by 1, so minus 3/2 becomes minus 1/2. But I need this minus 2 factor out front also because we're dividing by this power, okay? So we're going z squared to z squared plus r squared in that guy. Okay. So now I have a 2 here and a 4 here. So I'm back to having a 2 on the bottom. I have a negative sign here, I'm going to pull it out. So I have minus z sigma divided by 2 epsilon naught. And, okay, I'm just going to go ahead and plug in the top limit, which is u to the minus 1/2, where this is what we plug in for u. So it's z squared plus r squared to the minus 1/2 power. Plug in the bottom limit, that's going to be minus z squared to the minus 1/2 power. Okay? I think I need a new sheet of paper. I ran out of space here, so let's just keep it going. The rest is just some algebra to clean up this expression, okay? That's all we're doing, is just sort of trying to write this in a nicer looking way at this point. All right? So let's do that. If I have a 1/2 power, what does that mean? And if I have a minus 1/2 power, what does that mean? It's a 1 over a square root sort of thing, okay? So here, I have Ez equals minus z sigma over 2 epsilon naught. And I have 1 divided by the square root, z squared plus r squared, and then minus 1 divided by the square root of z squared. Okay? I can get rid of this minus sign here by just switching the order of these two terms. You see that? So in other words, I can write that as z sigma divided by 2 epsilon naught. And then now this will be my first term. And it's just 1 over z, because if I have z squared and then square root, it's just 1 over z. And then I have minus 1 over square root z squared plus r squared. All right, last thing I can do is just take this z that's out front, just multiply it into the parentheses, which gives me sigma over 2 epsilon naught. Now I'm putting the z inside the parentheses, which gives me z over z, which is 1 for the first term, and then minus z divided by square root z squared plus r squared in the second term like that. And that's where we're going to stop. You know, I could keep writing it in different ways, but we'll just stop there. Okay? So that was another example. And here's the, oh yeah,
Just a second.
sure thing. Yeah, if you need a minute, it's up there. I'm also going to save these papers, so at the end of class, you can come and look at these at the front of the room. Okay? All right, any questions? We can move on from there. So the rest of the lecture, and I hope we can get through all this, is to take this result, which is for basically a plate of charge, and do some things with it. See, like, how far can we stretch this result? How can we apply it to different situations? Okay? So let's get to that. So this is our result. Remember, x and y components of the electric field here are both 0, meaning the electric field is only going in the z direction like this. Okay? And the electric field in the z direction is given by this expression that we just derived. Okay? So with that as our result, I'm going to throw a little more calculus at you. Taylor series. Okay? Who remembers Taylor series? All right, if you took Calc 1, you've seen it. It may have been a while, so I'm just going to remind you how this works, okay? So basically, Taylor series can be thought of as a way to approximate a function. So if I have a function f of x, I can write it as an approximation given by the Taylor series. The Taylor series is actually just a polynomial sum, okay? And it goes on infinitely. So there's a x term, there's an x squared term, x cubed term. It just keeps going. That's what I mean by an infinite polynomial sum, okay? And there's a way to get it, which I'll show you here. Before we get to this equation, I just want to remind you that when it comes to Taylor series, you have to pick a point or a value of x that you're plugging in, okay? In other words, I can make an approximation for my function f of x as long as I'm staying close to some particular value of x. So for our purposes here, we're going to say we're going to expand around x equals 0. We're going to stay close to x equals 0 in this approximation. So how do we do that? Well, we take f0. What does that mean? What does it mean to say f0? 0. Just plug 0 into the function. That's what we get out, right? The next term is f prime 0 divided by 1 factorial. So what does f prime 0 represent? Yeah, take one derivative, plug in 0, and you get this number in the front, okay? But that's multiplying x. Okay, so we'll have just a number times an x term. Our next term is going to be x squared, but there's some number out front, in front of the x squared. That's f double prime 0 divided by 2 factorial. So that's the pattern, okay, for the Taylor series. Now, fortunately for us, whenever we're going to do a Taylor series, we're not interested in getting a super precise Taylor series. In fact, we're just going to keep what's called the leading order. Okay, so let's really think about this. We're expanding around x equals 0, right? That means x has very small values, a lot less than 1. We can assume whatever x is, it's much smaller than 1. What happens if I take a very small number and I square it? I get even smaller, right? Like 1 over 10, when I square it, becomes 1 over 100. What if I cube a very small number?
Really small.
even smaller than that, right? So if I take higher and higher powers of small numbers, we agree those are going to give us really small results out, right? So the point is, all of these high powers, like x squared, x cubed, and so on, those are all going to be very small numbers. And what's going to kind of dominate in the series are the first couple terms. Those are what we call the leading order terms, okay? So oftentimes what we can do is just take a look at the whole series and just only look at the first term that's non-zero and assume that everything else is small enough that it can be ignored to a pretty good approximation, okay? And when we do that, we can simplify how a function looks. We can take a really ugly looking function like the one we just wrote down in the previous example, and we can make it look simpler and nicer. That's the whole point of this part. Does that make sense? Okay, so we're going to try to do that. Consider the previous example. Remember, we had a uniform disk of charge sitting in the xy plane, and then at some point z, above the center of the disk, we calculated, it was very painstaking, this result. Ez is equal to sigma over 2 epsilon naught times blah, 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 right? So let's do a Taylor series expansion about that, keeping only the leading order term for two different cases, okay? So this is the first case I want you to think about. The first case we're going to think about is when z is much less than r. Remember, r represents the radius of the disk, okay? And z represents how far off the disk you're going. So in other words, if we're staying very, very close to the disk, then this would be true. Does that make sense? So z being a lot less than r is the case where you're not moving that far away from the disk. You're staying very close to it. We call that the near field limit, okay? So let's work out what our expression goes to in this near field limit. So we're gonna do it on paper, and then we'll put the result up on the screen. Okay, so we're starting here with the previous result, okay? And I'm gonna slightly rewrite it. So we have the same constants out front, sigma over 2 epsilon naught. This is still 1, but then I have minus this whole thing. And I'm going to, like I said, write it in a slightly different way. So I have a z on the top. On the bottom, what I have is a square root of z squared plus r squared. What I'm going to do is try to pull out a factor of r squared from that. So in other words, if I have r squared in the front, I'd have to multiply that by z squared over r squared to get back to where I was, right? And if I'm pulling out an r squared, just plus 1. But that whole thing is under the square root, which is like saying 1/2 power. Okay? So that's not a very good 1/2. Here, 1/2. Okay, sound good, right? Well, let's think about it. I have r squared to the 1/2 power on the bottom, right? That's just r on the bottom, isn't it? Okay, so sigma over 2 epsilon naught, 1 minus, I'm going to write it as z divided by r, like this, on top. The point is we have an r factor on the bottom. I'm just collecting it right here with the z term, okay? Then what are we left with? We're left with z divided by r squared in this parentheses, plus 1 to the 1/2 power. Okay? So what I'm going to do, because I see that I have z divided by r appearing twice, I'm just going to call that my new variable. I'm going to say let x equals z divided by r. And remember, we're dealing with the limit where z is much, much smaller than r, aren't we? So what can I say about x? In other words, I'm taking a very small number divided by a very large number, right? So it's small, it's like much less than 1. If I'm gonna label this as x, x is a very small number, much less than 1. Okay? So now here we're gonna bring in this Taylor series. The thing in brackets, the overall set of brackets out here, I'm not gonna copy that down again, I'm just gonna say brackets, that thing. What does that equal? It's 1 minus, I have x on top, that's my z divided by r. And on the bottom, I have square root x squared plus 1, basically, right? That's the thing I have in brackets if I write it in terms of x. Okay, well, what I'm going to give you is the Taylor series for this whole thing. Around x equals 0. We're not going to calculate it, it takes too much time. I'm just going to tell you what the Taylor series is, okay? The first term is x squared divided by 2. The next term is minus 3x to the 4th. I'm sorry, scratch that. I'm looking at the wrong page here. The actual Taylor series here is 1 minus x plus x cubed over 2. And it keeps going forever, right? But the thing is, we only are going to keep the leading order term. Which is to say, we're just going to keep the 1. Everything besides that 1 is going to be a very small number. So it's a really good approximation to say that this whole Taylor series is about equal to 1. That's really useful because we're saying as long as we're really close to the disk, this whole thing in brackets is just approximately equal to 1. That's a much easier expression to deal with. Okay, so in other words, EZ is approximately equal to sigma over 2 epsilon naught times just 1. Okay? That's an important result. If you're very close to a disk of charge or a sheet of charge or any kind of charge spread out over an area, as long as you're very close to it, that's the electric field. Okay, it's a pretty simple result. Much simpler than what we had before. So the result is, when you're very close to the disk and the near field limit, EZ is approximately equal to sigma over 2 epsilon naught. And actually, let's just think about that for a second. You know, epsilon naught is just a constant, isn't it? And so is sigma. Sigma just tells you, you know, how much charge there is per unit area. There's nothing in this expression that depends on a distance, right? So as long as you're pretty close to the disk, what we're saying here is that the E field is roughly constant, okay? And it's equal to this quantity here. Okay. The other case that we want to look at here is what we call the far field limit. So let's imagine that we're not right up against the disk, very close to it, but instead we're very far away from it. How can we say that we're far away from it? Well, remember, Z is how far away we are from the disk. R is the radius. So if Z is much bigger than R, it's kind of the opposite limit now. That's what it means to be very far away for our purposes. Okay, so Z is much, much bigger than R. And we're going to call that the far field limit. Okay, let's go through it, and then let's see if we can make sense out of the result that we get. Okay. So we're starting with this. EZ is sigma divided by 2 epsilon naught. And then in brackets, we have 1 minus Z over Z squared plus R squared to the 3/2 power. That's just the result we derived in the last example. Okay? But now what I'm going to do with that is rewrite it. And basically, I'm just going to slightly change the way I'm writing this second term here. On top, I have Z, of course. But on the bottom, I'm going to try to pull out a factor of z from the parentheses. So let's see how that looks. I'll have z squared times 1 plus r squared over z squared. So you agree I can write z squared plus r squared like this if I wanted to, just by pulling out a z squared. And if that whole thing is, I'm sorry guys, I meant to say this is the 1/2 power. That's the result we got, not 3/2. But anyway, that's what we can do, right? So to kind of simplify this, we have sigma over 2 epsilon naught times 1 minus, I have a z on top, but on the bottom, I have a z squared to the 1/2 power. That's just like having z on the bottom, right? So that's just like z over z, which is just 1. And then all we're left with is 1 plus r divided by z squared, that's this thing, to the 1/2 power, which I can write as the following. Sigma divided by 2 epsilon naught, 1 minus 1 over 1/2 power is the same as square root, so I'm going to write it like this. 1 plus, I'll call it x squared, where x is just r divided by z. Okay? So we clear on how I was able to write it this way. So again, if we take a look at the thing in brackets, I'll tell you what the Taylor series is. We're not going to calculate it. Just tell you what it works out to if you go through that process. This Taylor series is x squared over 2 minus 3x to the 4th over 8. And then there's some other terms. I'll just write the next one. It's 5x to the 6 over 16. And it just keeps going, right? All Taylor series go on forever. But we only care about keeping the leading order term. So in other words, I'm only keeping from this Taylor series the x squared over 2, because I know that since x is a small number, I'm taking higher and higher powers of x, I'm just getting smaller values for these later terms in the series, right? So just keeping the leading order term is a pretty good approximation. Okay, well, that means EZ is the thing out front, which is sigma divided by 2 epsilon naught, times the thing in brackets, which we're saying is x squared divided by 2, right? And let's just remember, x is, r divided by z. So I'm going to put back in r divided by z for x. So I'm going to have sigma, I'll have an r squared on the top, I'll have z squared on the bottom, because x squared is r divided by z. And then I'm going to have a 4 epsilon naught right there. Yeah, I think that's right. Okay. So the last thing I'm going to do is make one more substitution here, just to rewrite it in a kind of suggestive way. Remember, sigma is just a charge per unit area on the disk, right? So it would be the total charge on the disk divided by the total area of the disk, wouldn't it? We agree? How do I write the area of a disk? It's a circular shape. Sorry, you can't see that. Pi r squared, right? In other words, sigma, charge per unit area, is just Q, the total charge on the disk, divided by pi r squared. So I can make that substitution too, huh? So on top, I have Q divided by pi r squared, multiplying r squared, and then dividing 4 epsilon naught z squared. So r squareds cancel, and I'm left with Q on top, 4 pi epsilon naught on the bottom, and then z squared as well. Does this look familiar? What is that? That's just Coulomb's law, right? Z is what we're representing as the distance to the charge, right? Q is how much charge you have, and K, the constant, is the same as 1 over 4 pi epsilon naught. So this is just Coulomb's law. When does this apply? It applies when you have a point charge, right? This is important. We have a disk, but we're really, really far away from it, right? As far as we're concerned, it just looks like a point charge. And the field it creates just looks like a point charge. Does that make sense? That's generally going to be the case if you have a charge distribution and you're very far away from it. It's just going to look like a point charge. Okay?
Is the reason why your sigma is Q over A because it's constant?
So this is just definitions. Sigma is charge per unit area. That's what it means. So I just wrote it that way and tried to substitute some things out to get to this point. Yeah. Okay. So what did we learn? We learned that very far away from the disk, the electric field comes down to sigma r squared over 4 epsilon naught z squared. We did the work for that, right? And we also said that could be written alternatively as q over 4 pi epsilon naught z squared, which has the form of Coulomb's law. In other words, this is the same E field we would expect if instead of a disk of charge, it was just a point charge. It's exactly the same formula. So the lesson is, any charged object, as long as you're very far away from it, is going to appear like it's a point charge. It's going to create an electric field as if it was just a point charge. Okay? All right. So I think this is the last thing we'll end on. That result we got, that when you have a disk of charge and you're very close to it, the electric field is roughly constant and it can be approximated as sigma over 2 epsilon naught. I want to just explain like how far you can extend this result. When can you use it? Okay? So the fact that we started with a disk is not super important for this result. In other words, if you had a rectangular sheet of charge and you were very close to it, this result would still apply. If you had some other crazy shape, but it's a sheet of charge and you're very close to it, this result would still apply. Okay? In fact, if you had an infinite sheet of charge, this result would apply as well. Okay? So just keep in mind that this result will be valid for all these different cases. So one thing we're going to do a lot in this class is imagine an infinite sheet of charge. Let's focus on that. Okay? And let's say the sheet has a positive charge, just so we can visualize something. If we're looking at that sheet from the side, okay, so we're looking at it kind of edge on like this, what will we see as far as the electric field is concerned? Electric field lines point away from positive charges, right? So what we'll see is all of the electric field lines pointing away from the positive charge on the sheet. The lines are just coming straight off the sheet like this. This tells us the direction it's going, just going away from the sheet. Okay? As far as the magnitude, this result applies. Okay? So whenever we deal with an infinite sheet of charge or a finite sheet that you're just really close to, this is what the situation looks like. Okay? We got here by thinking of it as a disk, but it's actually going to apply more generally, just any kind of sheet. So that's all we have time for today. I'll see you next week. Remember, we have no lab today or Friday, so I'll just see you next Monday. I'll stick around for a bit if you have questions.